Okay students, now let's start with a new chapter, that is the classification of soil. Okay, in this we'll be classifying different types of soils named as sand, gravel, clay, silt, organic soil, and peat is also a part of organic soil. So we'll be basically nomenclating all these soils, and basically we have different formulas and different like combinations which we have to put up so that we can classify different types of soil. Okay, so let's start with the classification of soil. So write down why, because first of all we have to know that why are we actually classifying the soils. You should know why are you actually classifying the soils. So firstly, write down classification of soil means sorting the soil into the group showing identical behavior, comma, classification of soil is done on the basis of index properties of soil. So this is a very important point which I have mentioned, that the classification of soil is basically dependent on the index properties of the soil. Okay, why? Because if it is a clay, it will depend on the water content. Water content we have basically studied in the last class, and we studied consistency limits, that are nothing but called as the Atterberg limits. In that I defined many liquid limit, plastic limit, shrinkage limit and all. So all those aspects are very important in classifying a fine-grained soil. Now, if we are classifying a coarse-grained soil, that will be dependent mostly on the grain size of the particle. So the size of the particles are very much required when you are classifying a coarse-grained soil. Okay, so let's start the classification of soil, and in that we'll be starting up with the gravel. So before that, you can write down, just write down, classification of soil is done on the basis of index properties of soil. The most commonly used properties are the grain size distribution and plasticity. Okay, grain size distribution is done for the coarse grained soil, whereas the plasticity indexes, or the different indexes which we have studied, is nothing but depending mainly on the fine grained soil properties. Okay, so let's start with classification of gravel. So how would you say that a soil is gravel? So we'll write down gravel. So that will be nothing but denoted by G. So gravel is nothing but a particle. First of all, it is a coarse-grained soil. That is very important. Gravel is a coarse-grained soil. Now, we know that a soil can be termed as a coarse-grained soil if it is more than the 75 micron or not. So firstly we have to know that whether the soil is greater than 75 micron. So if it is greater than 75 micron, it is obviously a coarse grained soil. Okay, so if a soil is having sizes more than 75 micron, it is a coarse grained soil, and if it is finer than 75 micron, it is a fine grained soil. Now here also we have two limits. One is the 4.75 mm limit, and here after this we have 2 micron. Okay, so you can say 2 micron, 0.2 micron. What we have is the fine grained property. Okay, so the soils which are very well imagined on, or like directly we can see it and we can directly say that it is a fine grained soil. So basically when we are defining different types of soils, we should have their size in contection. So if we have the size in contection, will be very much noticeable, and we can very well identify whether the soil is, this is 2 micron. So we have one range here as 2 micron, another we have as 4.75 micron. So here, if the soil is greater than 75 micron, it is coarse grained soil. So if it is above than 4.75, it is gravel, and if it is below, it is sand. And here we have silt, and here below this we have clay. This is the general saying, but you cannot generally define and say that okay, this soil is all the 100% of the soil material is greater than 75 micron, or is greater than 4.75 mm, or is less than 2 micron. So we cannot say that generally, because every soil has different mixtures of different soils that we have to consider. Now, so if my soil is majority of my soil, how you define is, like if majority of the soil is greater than, that is more than 50% of the soil is greater than 75 micron, it is a coarse grained soil. Okay, the basic says this: if more than 50% of the soil is greater than 75 micron, then the soil is a coarse grained soil, and if 50% of the soil is less than 50 micron, it is not a coarse grained soil, it will be a fine grained soil. Now, if out of those 50%, which is greater than 50% means, let's suppose 51%. So if more than 51% is greater than 75 micron, obviously it is a coarse grained soil, but whether you will term it as gravel or sand, that will depend on, out of those 51%, how many are greater than 44.75 mm. So if greater than 50% of 50%, 50% of 51%. So if it is 26.5, it is greater than 26.5% of total, then it will be gravel. And if it is less than 26.5%, that is a 50% of, so 25.5% of 51%. So then it will be a gravel, otherwise it will be a sand. So let's write down the definition of gravel first of all. Write down: if more than 50% of coarse fraction, in bracket write down greater than 75 micron, is retained on 4.75 mm sieve. Is retained on 4.75 mm sieve. The soil is designated as gravel. Okay, that is very important and easy to understand. Okay. Okay students, now I have taken an example here. What is happening is greater than 4.75 mm we have 400 grams. Between 4.75 mm and 75 micron I have 300 grams and 300 grams are passing. So total soil quantity is equals to 1000 grams. Okay, so out of 1000 grams I have 400 grams which are which are above, which are retained on 4.75 mm sieve. 300 are lying between 4.75 and 300 grams, and 300 grams is passing the 475 micron sieve. That means I can say that the coarse fraction equal to 700 grams and fine fraction is equal to 300 grams. Now, coarse fraction is 700 grams, which is actually more than 50% of the whole soil. Okay, because this is greater than what? 500 grams, which is the 50% of 1000 grams. So obviously this soil is actually coarse grained soil. So the soil is, I can write down, the soil is coarse grained soil. Okay, because 700 grams is greater than 400 grams, sorry, before more than 75 micron I have 700 grams, total 300 plus 400, so it is obviously greater than 500, so this will be a coarse grained soil. Now out of coarse grained soil is either it is gravel or sand. We'll get to know by checking out the fraction which is retained on 4.75 mm or not. So we'll say that okay, 400 grams is greater than 50% of coarse fraction is what? 350. So 350 gram implies the soil is gravel. So that is how you find out whether the soil is a gravel or a sand. Okay, you check the coarse fraction, and in that coarse fraction, if 50% is greater than 4.75 mm, so therefore it will be a gravel. If it is less than, then it will be a sand. Okay students, now if I just change the data here, so now I can say that here 300 plus 400, again 700 is greater than 500, therefore it is, fine fraction is again 300 grams. If this is the case, so we can say that the 50% of the soil is again greater than the 475 micron sieve, therefore the soil is coarse grained soil. Now out of coarse grained soil, it is fine, it is sand or gravel. How can we check? See here, this 400 gram, this 400 gram is now greater than 350 grams, therefore the soil is sand. Very easy to understand that the soil is a sand here. Why? Because more than 50% of the coarse fraction is passing 4.75 mm sieve and retained on 75 micron sieve. Okay, very carefully you can understand that. Okay students, next we have here in classification of soil we have silt. Silt is denoted by M. Okay, so write down soil passing 75 micron sieve and identified by slightly plastic behavior regardless of moisture content. Okay, then next point, write down little or no strength on air drying. So what we can say is that yes, silt is a fine grained soil, but cohesion is really less. So when you pass air through it, on air drying there is not much of strength which is present in the silt. Therefore we can say that it is a fine grained soil, but yes, there is no or little strength of air drying. It is denoted by M. Next, write down fourth, we have clay. Okay, so in clay what I will be saying is the soil passing 75 micron sieve and identified by the following behavior, So here the first property is A, write down, shows plasticity within a range of moisture content. So shows plasticity within a range of moisture content. Then write down second point, considerable strength on air drying. Considerable strength on air drying. Okay students, now let's move on to the next one, that is fifth, the organic soil, denoted by O. So the organic soil, we already know that it has a characteristic which says that here the soils are generally dark in color and pungent in smell. So just write down organic soil, in that write down So here we are basically discussing how we can directly see and predict whether which kind of soil is this. So write down dark in color and pungent in smell. Next write down peat. Peat is denoted by PT. Peat is denoted by PT. This is also part of organic soil, but we nomenclate it a different way. So write down peat. Write down organic material with fibrous organic matter, and spongy in consistency. That is very important because it is made up of fibers, so it is very, very spongy. So spongy is what we are calling that particular matter, and if the substance is very spongy, we can say that it is peat. Okay, now let's move on. Okay students, now let's study the plasticity chart. This is basically used for providing the nomenclature for the fine grained soils. Okay, this is basically done for the fine grained soils. So what does the plasticity chart tell us is, and this is the plasticity chart. Here we have one A line. This is an A line which is passing through water content 20%. So that's why the equation of the line is IP, because here y is equals to mx plus c kind of graph is this. So we have IP is equals to 0.73 WL minus 20. So this will be giving us the IP value. Okay, this will be giving us the IP value. So what we'll be doing will be like here, IP will be calculated by this particular method. Next. Now, as I have created this IP value, also there can be a different IP value, because if the soil is given, if WL and WP for that particular value is given, so we can calculate the actual IP for the soil. That will be nothing but WL minus WP. So here we'll compare this. If this point IP comma liquid, or the, here what we are plotting is not just the water content, here we are plotting the liquid limit values. We are plotting the liquid limit values, and if the liquid limit is between these two, so this point, this is the x coordinate which we'll be getting, and we'll be getting a y coordinate according to this. So if we can very well measure that the point will be here, or wherever be the region. So if the point is here, it is of clay. It is of clay nature, of intermediate compressibility. This is giving us the compressibility of the material, because more the water content, more compressible it is, because here we very well know that liquid limit is proportional to compressibility. So if the plasticity is more, obviously it will be clay, because IP more, it will be clay, and if the plasticity is less, it will be silt or organic. This is nothing but organic soil of intermediate compressibility. This is organic soil of high compressibility. This is silt of low compressibility. L means low, I means intermediate, H means high compressibility. And M is nothing but silt, O is organic material, and C is clay. So I hope you understood this plasticity chart. So this is very, very important. We'll solve few problems on this. Then we'll get to know about the basic plasticity chart. So let's move on and take a few problems. Okay students, now let's take a few problems on the previous year's GATE. The question is from GATE 2016, Set 1. GATE 2016, Set 1. And it is for 1 mark in civil engineering. Okay, the question says a fine-grained soil is found to be plastic in the water content range of 26 to 48%. Okay, the soil is plastic within the range of 26 to 48%. So that means that its WP is nothing but 26%, because plastic is between WL and WP, that is 48%. Okay, so now if I want to calculate my IP of A line, that will be what? That will be nothing but 0.73 into WL. What is WL? 48. minus 20, that is coming out to be 20.44%. And actual IP is coming as, that is nothing but WL minus WP is coming as 48 minus 26, that is coming out to be 22%. So actually this is greater than 20.44%. That means it is above the A line. Okay, so here our IP value is coming out to be 20.22%, which is greater than 20.44%, which you have calculated from the IP line, this line equation. It is nothing but y is equals to mx plus c, and if you just put the value of liquid limit here, you will get the value of what? IP through the A line. Now if you see that this IP is coming out to be greater than 20.44%, that means it is above this A line. That means it is a clay particle. It is a clay particle, that is more than sure to us. Now we have to check its compressibility. I told you that compressibility is directly proportional to liquid limit. It is only dependent on the liquid limit, and if you check here where the liquid limit will be lying, 48% is my liquid limit, that will be lying here, 48%. So that will be in intermediate compressibility, and also it will be clay. So this will be my particular, the soil is right on, the soil is CI. Okay, the options given were CL, the options given were CL, ML, MH and CI. So the correct option will be CI, because it is of intermediate compressibility and it is obviously a clay because its plasticity is more than the value which is given. Next question is from GATE 2010. That is a GATE 2010 question. Of the marks awarded to the question is 1 mark, and it is from civil engineering. The question says a fine grained soil has liquid limit of 60 and the plastic limit of 20. Okay, the liquid limit is given as the 60 and plastic limit is given as 20. Full stop. As per the plasticity chart, according to IS classification, the soil is represented by the letter dash. So that you have to find out. This is again a very simple problem which is being given. So firstly we need to calculate the actual IP, then the IP according to the A line. So what we will be saying is that IP according to A line will be calculated because the liquid limit is already given. So the liquid limit is given and the plastic limit is also given. So if I apply IP is equals to 0.73, liquid limit is given as 60 minus 20, this will be giving me 29.2%. And if I calculate IP equals to WL minus WP, that is nothing but 60 minus 20, that will be giving me 40%, which is again greater than 29.2%. Therefore the soil is clay and its liquid limit is lying now here 60%. So it will be in this region and obviously it is above the A line, therefore it will be CH this time. The soil is CH. So very simple questions that are asked in GATE from this topic, you can very well solve it with the help of the plasticity chart. We'll take a few more problems now. Okay students, now let's take up a new problem that is from GATE 2009. Okay, the problem is from GATE 2009 and the question says that the laboratory test results of a soil sample are given below. Okay, the question says that percentage finer than 4.75 mm are 60%. So below 4.75 there is 60%. So that means 30, and therefore this will be net will be 60%. And also they are saying that percentage finer than 0.075 mm is 30%. So net below this is 60% and below this is 30%. Therefore sand will be also 30%. Next what they are saying is that liquid limit is 35% and plastic limit is 27%. That's it. That is what is given. They are saying that classify the soil. Very easy question. Because this is 30, this is 30, obviously this gravel will be 40%. So as we can see that out of total, below 0.075 is nothing but what? We have 30%. So more than will be our 70%, which will be greater than 70% is greater than 50%. So therefore, it is coarse grained soil. Now, out of this 70%, 40% which is greater than 35%, 40% is greater than 35%, which is the 50% of the 70%. Because therefore it is implied it is gravel. So we got the main nomenclature as gravel. Now there are some fines. The fines are of huge quantity, so we have to imply them also in our nomenclature. So if the fines greater than 12%, we have to, so they are included, okay, in nomenclature. So they are greater than 12%. So our fines are 30%. So therefore that will be used. And as we calculate the IP will be 35 minus 27, which is given, liquid limit and plastic limit, so that is nothing but 8%. And IP of A line is 0.73 into liquid limit minus 20, liquid limit is 35%, so it will be 10.95. So we can see that the IP is coming out to be less than IP of A line, therefore it is below the A line, therefore it will be silty in nature. Unless and until specified, it is organic material. Therefore they will say that it might be spongy or it might be dark in color or pungent in color. We will write it is silty in nature. So our main soil nomenclature will be GM. Silty gravel. It should be silty and it is also mainly it is gravel. So the first name is nothing but its whole nature, and because it is the whole thing is gravel and its property is silty because we just tested from the A line. Okay, next problem is, please note on the question. The question says, sieve analysis on a dry soil sample of mass 1000 grams showed that 980 grams and 270 grams of soil passed through 4.75 mm and 75 micron or 0.075 mm sieve respectively. That means that if I draw this table, so I'll find out that this is 4.75 mm, this is 0.075 mm. So what are they saying is 980 gram passes through this part. So 980 gram is passing through 4.75 mm sieve and 270 gram pass through 4.75 mm sieve. So 270 gram passes, that means that this is the coarse, this is fine grained, this is coarse grained soil, this is fine grained soil. So the net passing through the 0.075 mm is 270 and here it is passing is 980. That means this is inclusive of this also. So that means that 270 by 1000 into 100 will be giving me 27%. So 27% are fine grained soils, that is inclusive of silt and clay, and if out of this net passing through 4.75 mm is 980 by 1000 into 100, that is equal to 98%. So passing 4.75 mm is 98%, therefore 27% will be this one. So this will be what? This will be 98 minus 27, that is coming out to be 71%, and rest, which is nothing but approximately 1%, will be gravel. And this is sand, this is gravel, this is sand, this is total fine grained soil, silt, that is M or C, which can be M or C. This is my main nomenclature which I have done corresponding to the first statement what they have told. Next what they are saying is that liquid limit and plastic limits of the soil fraction passing through 425 micron sieves are 40% and 18% respectively. They have given the liquid limit and the plastic limit as 40% and 18%. So my IP will be, actual IP will be 40 minus 18, that will be equal to 22%. Because liquid limit is given as 40% and plastic limit is given as 22%. So I can very well calculate the IPA as well. IPA will be 0.73 into 40 minus 20, that is coming as 14.6%. Now, as you can see that the soil is a coarse fraction because 72% is greater than 0.075 mm. On after that, 71% is this much only. Obviously, the soil is sand. The soil is sand, but its fine fraction is also huge. It is more than 27%, is greater than 12%. So it will be used in the nomenclature, and its nomenclature will be because 22% is greater than 14.6%, it is clayey. So it will be sand and it is also clay in nature. So it will be, soil will be SC, clayey sand. This is very, very important. Okay students, now let's discuss the clay mineralogy and the soil structure basically. So here basically mineralogy is basically affecting the properties of fine grained soil because they are composition of what? The chemical weathering. There are chemicals which are provided in the rocks, which they are chemicals which are coming due to the seas, glaciers, acid rain, whatever it be. So the chemicals comes into the rock and therefore the weathering happens, and therefore soils which are formed are called as fine grained soils, and therefore their mineralogical composition is becoming very important in classification of their in actually studying the properties of that particular soil. Now what we can say is that firstly this chemical composition or the mineralogical composition is basically affecting the fine grained soils. This point is very well understood to us. Now here we have time and again I have told you that the soil, which is a clay, is mostly affected by the water content. So because the soil is primarily of a plate like structure which has negative charge on its face, therefore what happens is the water molecule which has two hydrogen charges, that is plus charge, are attracted towards this particular negative charge on the clay plate. Therefore water is attracted towards the system. Moreover, it has a large specific surface, clay, because it is very small sized mineral. So when small sized particles are there, they have large surface area, they can imbibe more amount of water. Therefore water is actually a very important particle which is present in the voids of the clay mineral, and it affects its property to a large extent. Okay, so let's write down the theory behind it. Write down mineralogical composition of grains. Mineralogical composition of grains hardly affect the engineering properties of coarse grained soil. Mineralogical composition of grains hardly affect the engineering properties of coarse grained soil. Full stop. However, the mineralogical composition significantly affects the properties of fine grained soil. Okay, the properties of fine grained soils are significantly affected. That is a very big statement. Okay, next write down chemical weathering of rocks. Chemical weathering of rocks result in formation of colloidal sized particles known as clay minerals. Chemical weathering of rocks result in formation of colloidal sized particles known as clay minerals, okay, which is sized less than 2 micron. Size is less than 2 microns. Next write down most of the clay minerals have plate-like structure, having high specific surface. Because of the large specific surface, large quantity of water gets attached to the clay. Then write on thus water content of clay soil is generally more than that of the coarse grained soil. Okay, therefore the water content of the clay soil is more than the coarse grained soil. Okay, now the clay minerals are basically made up of two different parts. Okay, there are two different things which are clay is made of. First is the silica sheet. Okay, first is the silica sheet. There are silica particles like this, and it is also called as the tetrahedral sheet. This is the tetrahedral, or it is called as the silica sheet. These are two types of minerals that are present. Or we have octahedral, like this, octahedral sheet, that is called as the gibbsite. It is also called as the gibbsite or octahedral sheet. So these are the two basic molecules or two basic structures in which the clay particles are formed. This is called as silica sheet and this is called as the octahedral sheet. So write down atomic structure of clay minerals. Atomic structure of clay minerals are made of two fundamental crystal sheets. First, tetrahedral sheet, and second, octahedral sheet. Okay students, now let's discuss few types of clay minerals. There are basically three types of clay minerals. The first of them is kaolinite. Okay, so I told you that the basic components of a clay mineral are two. First is the gibbsite sheet, that is made up of aluminium, that is alumina sheet also, that is also called as alumina or octahedral sheet. Then we have the silica sheet, that is nothing but made up of silica. Okay, so when we combine the aluminum and silica sheet, these are both combinedly called as silica gibbsite sheet. Okay, these are called as the silica gibbsite sheet. So it is, first is kaolinite, which is made up of one silica gibbsite sheet combined with other silica gibbsite sheet. So this is called as 1:1 clay mineral. Okay, this is the basic important thing which we have to understand, that the kaolinite is made up of 1:1 clay mineral and is composed of one silica and one gibbsite sheet. Now what I want to understand is, like, what is the bonding parameter between these two sheets. So here we have basically the hydrogen bonding. We have hydrogen bonding between them. Hydrogen bonding, which is a very strong bond. This is a very strong bond, hydrogen bonding. Why? Because these two minerals are composed of alumina and silica, and these are combined with the negative charges present over here are O minus. This in detail which we don't have to understand. Just we have to understand that hydrogen bonding is there between these two particles, which are causing the two particles to be very close to each other and with attractive forces. So what happens is, when two particles are very close to each other, there cannot be an external agent which can get into that. So what we will be saying is that this hydrogen bond is very strong to diminish. So we cannot break this hydrogen bond very easily. So if we cannot break this bond, we will not be intruding the water in it. So here we will be saying that its water content will be low because the water cannot break the bond and get in the voids. Okay, so water content will be very low. It will be of low plasticity and low active mineral. More the water it can take, more it can swell, more it can shrink. Therefore the soil is more active. This is very important. So here the bond cannot be broken very easily. That's why the penetration of air and water is not very easy. Therefore the voids are pretty much very low in this type of mineral, and that's why we'll say that it is very less active mineral. Please write down. It is a 1:1 clay mineral. 1:1 means one silica gibbsite is combining with other silica gibbsite sheet. Okay, so write down, it is a 1:1 clay mineral, full stop. Then write down the bonding forces between one silica gibbsite sheet, and another silica gibbsite sheet, is hydrogen bonding. Which is very strong. Okay, thus there is very little tendency in the internal layers to swell or to allow water. Full stop. Thus kaolinite is least active mineral. Because it does not swell. Okay, so as you would have heard that we make China ware material. Okay, in Hindi we call it chini mitti ke bartan, isn't it? We call it chini mitti ke bartan or China ware in English. So we make most of the China wares with the help of kaolinite. So the kaolinite is used because it cannot swell or shrink. So that will be very easy to simplify, and these are the materials which are used when we do not want our material to swell or shrink. Okay students, now let's move on to the next mineral, which is Montmorillonite. Now what happens is, this is made up of 2:1 because one unit has 2 silica and 1 gibbsite sheet. So that is 2:1 mineral will combine with another 2:1 mineral, and that will form Montmorillonite. Next, what is the most important point over here is, these are composed of weak van der Waals forces. Van der Waals forces are very weak forces, so they are very easily breakable. So water can introduce into the system very easily. Very easily the water will come in, and therefore it will swell or shrink the molecules, and therefore it is the highest or the most active mineral possible, because it has the voids which are filled with water. It can take a lot of water because its bonds are very easily breakable. That is what the mineralogical composition of Montmorillonite is all about. Please write down. Write down. It is a 2:1 clay mineral. It is a 2:1 clay mineral. Full stop. Montmorillonite have largest specific surface. Yes, it will have largest specific surface. Why? Because more the water into the system, more is the specific surface. Okay? Then write down bonding forces between the units. Bonding forces between the units is weak van der Waals forces. Is weak van der Waals forces, hence large quantity of water, and exchangeable cations can easily enter between the layers, causing the layers to be saturated. Full stop. Because of above conditions, because of the other and above conditions, Montmorillonite is the most active mineral. Next, write down. Bentonite is a Montmorillonite clay. Bentonite is a Montmorillonite clay derived from volcanic ash. Okay, bentonite is a Montmorillonite clay derived from volcanic ash. Okay. Then write down, in India, soils containing Montmorillonite minerals are commonly known as black cotton soil. So the black cotton soils are basically made up of Montmorillonite. Okay, the black cotton soils are first of all formed because they are said to be black cotton soil because these are highly active soils, because they have a lot of Montmorillonite in it. Moreover, cotton grows heavily in the soils which are having high active components. So therefore, it is termed as black cotton soil. Understood? Okay students, now let's move on to the next and the final material which we have is illite. So what is illite? Illite is again a 2:1 mineral which is having 2 silica components and 1 alumina. That is combined with other silica alumina sheet, and this in between there is a potassium ion which has a metallic bond between these two. So when metallic bonds are there or ionic bonds are there, they are not as strong as hydrogen bonding, but yes, obviously stronger than the van der Waals forces which are very weak. So in this illite, this is an intermediate it is having intermediate properties between clay and between montmorillonite and your kaolinite. So it will have intermediate properties between kaolinite and montmorillonite. Right now, it is a 2:1 clay mineral. Is a 2:1 clay mineral. It has substantial amount of extrusion of water into the system. Okay, water can very well intrude into the system. Full stop. Potassium ion bonds the two negatively charged surface. These are negatively charged surfaces of the silica sheet tightly. Okay, full stop. Then write down, it is lesser active than montmorillonite. Lesser, obviously it will be lesser active than montmorillonite, but greater than kaolinite. Okay students, now let's look at the next table which I have for you. Here the table is for the different types of soils which we studied. Well, first is montmorillonite, illite and kaolinite. We have represented their grain size, IP, dry strength and activity. See here, first let's look at the grain size. As we know that montmorillonite is the most active material, so obviously it will have the maximum activity. Then we have illite, and then we have minimum is for kaolinite, intermediate is for illite. Now, more activity means it can imbibe more water. More water is coming into the system and means it has more specific surface. And more specific surface means lesser size. As clay has more specific surface, therefore it has smaller size. Similarly, montmorillonite will have the minimum grain size because it has larger specific surface. It can take up more and more water from the system. Therefore, elite will be intermediate and maximum size will be of kaolinite. IP, more the water it can take, more the water it can throw out. So its plasticity is more. So its IP will be obviously more. So more will be the plasticity also intermediate and here minimum. Now more water it can take, more it can release and become dry. So more water into the system, and when it releases it off, the dry strength also becomes more. So more the plasticity or more the IP, more is the dry strength. That you have to keep in your mind. So the kaolinite will have the minimum dry strength, an activity you already know. So this table is very important. You will get some match the following and fill in the blanks type of questions on this. Okay students, now we have the clay structure. We have two different types of structures. One is called as the dispersed structure, one is called as the flocculated structure. So what happens is, when the repulsive forces dominate, we say that it is a dispersed structure. As we can see that the negative charges will be obviously repelling each other, therefore this water thickness or the net thickness of the system is high. So what happens is, this thickness is higher in dispersed case because the repulsive forces are dominating. Whereas in the flocculated structure, we have edge to face connection. Here we have face to face connection. You can say that face to face is there, and here we have edge to face connection. Okay, this is called as the double diffused layer. Double diffused layer, which will be more than, this will be more than obviously the flocculated one, because this is repulsion is dominated. Repulsion is dominating over here. Here attraction is there. Okay, so this can be, I can give you a day-to-day life example that when you have dispersed structure, that can be equated or somewhat similar condition of books. So one book is kept above the other, but they are repelling each other. So what happens is, when one book is kept above each other, the voids are very less. But if you try to put a book inside the book of another, so you open the page and then you flip it up, then one by one you flip it up like that if you draw it, so that will be having a lot of voids in between. So it is somewhat like this. So here what we can say is that the void ratio E is more, but here E is less, because it is packed one above the other. Okay, next thing is what? Like now I have packed the one book like that, one above the other, another is like the pages are turned like that, and then you have plotting it. Now if you apply forces in this kind of, when you have pages like that folded between each other, so what will happen when you apply the loading, shear forces or lateral forces, what will happen? In this case, these will slip, one book will slip above the other, but here as they are connected from page to page, what will happen? They will hold that things together because they will be having larger shear strength. That's why this is having tau is more, where tau is nothing but my shear strength. Here tau is less. Okay, double diffused layer is more in this. Why? Because more water can be taken, because repulsion is there, repulsion is more, so the water also can be taken away more rapidly. Therefore water content of this is also more, and here water W is less. So this is very, very important, the dispersed structure and the flocculated structure. Lots of 1 mark questions in GATE as well as other PSU and ES examinations are asked from this topic. So this is what you have to keep in your mind. If you just have this in your mind, you can solve any problem related to this chapter. Okay, I hope you understood this. Okay students, now let's start with the next chapter, that is the soil compaction. It is a very easy topic which we have to understand. This is nothing but called as the soil compaction. So soil compaction is nothing but you are trying to remove the air voids. Okay, the soil structure will be nothing but comprising of air voids and the water voids. But in general, compaction is done on a non-saturated system, that is a normal system which has air as well as water, and we generally try to remove the air voids in it. We are not concerned about water. Okay, here we use dynamic loading such that rollers and dampers to remove the air voids. Why are we doing it? Compaction is done because just to increase the total unit weight of the system. Okay, here we have to simply measure the compaction by gamma D value. Why? Because I'll give you a live example. Like if I am a contractor and if I want to make an embankment, so I'll give that contract to a company. So what I'll say is that I want the unit weight to increase, then I'll understand that okay, the compaction has been done. But what will he do is, if I just check the bulk unit weight, that is nothing but WW upon WS upon net volume. Okay. So if I check that, so if he increases the weight of water, if he increases the water quantity in that particular range only, in that fixed volume only, so that he can increase the gamma T. So what he will do is, he'll put the water and he'll put less soil solid. This will be less, water will be more. But if I want for embankment to stand still and to take up loads, what I need is, I need more soil solids. So he will cheat me in that regard if I check with gamma T. But now if I check with gamma D, I know that that is nothing but equal to WS by V. V is obviously constant for the system. If I want to fix a volume, I want a fixed volume and I want to say that compact me for this particular volume. So the volume is fixed. So now I will check gamma D and that is only dependent on WS. So he has to increase the WS now in order to give me a proper embankment that can stand specific amount of loads for a given condition. Okay, so now if I will increase my WS value, then only the gamma D value will be increased and then only my system will stand still and take up the loads which is required. Okay, so he has to increase the WS, he has to put in more soil solids, he has to dig more soil. Okay, so then only our work will be done and he will be paid accordingly. Understood? So whenever we are checking the compaction, the main thing which we have to keep in mind is the dry density. The dry density is the most important thing that should be checked. Next, please write down. Please write down. In order to increase the unit weight of soil, by forcing the soil solids, into denser state, thereby reducing the air voids because of compaction, full stop, the shear strength of soil increases, and hence the stability and bearing capacity of the soil increases. Okay, so as you compact the soil, its shear strength will also increase, and later on you will find out that if shear strength is increased, everything gets increased. So its compressibility, its bearing capacity, everything will be, compressibility will be decreased and your bearing capacity or the load taking capacity will increase. It will not be compressed now. Voids will be less. How will it be compressed? Its permeability will also decrease. water also will not pass through the system. So we can say that right on after this, the compressibility and the permeability of the soil reduces because of compaction. Okay, this is very, very important, that the permeability and the compressibility of the soils reduces because of compaction. Next, right on. Okay students, next write down, compaction is achieved by application of mechanical energy in the form of rollers, tampers, etc. On a partially saturated soil. So what we are trying to achieve is, like when we compact a particular material, so its initial stage, what is this thing is like, here we have air, water and soil solids. Okay, here we have air, water and soil solids. This is the initial case. So initially we have particular volume V1 and our Ws is this much, and this is WW and this is 0 watt weight. So net volume is V1. Now after compaction, what happens is, the air voids are decreased, therefore the air is now only this much, and now water is same what was there before, and the solids also are the same as before. So Ws is constant and the net V2 is different now. So the net volume V2 will be less than V1. This is very, very important. And that V2 less than V1 because only due to this part, this decrement in the volume of air. So here, if my gamma D1 dry unit weight in first case would have been Ws upon V1, this would be gamma D2 is equals to Ws upon V2. So if V1 is greater than V2, obviously my gamma D1 will be lesser than gamma D2, and we'll say that compaction is achieved. Okay, this is how the compaction is done, and this is how we use the techniques of rollers and dampers which try to compress the air voids. This is what the general compaction is all about. Now we'll look at basic difference between compaction and consolidation so that we don't have any confusion in the later on. Okay, so just write down. After this, write down. Compaction is quantitatively measured by the dry unit weight. Okay, compaction is quantitatively measured by the dry unit weight. Full stop. Because it is the dry unit weight, which indicates the packing of the soil. Okay, I already told you, because it is the dry unit weight which indicates the packing of the soil. Okay. Okay, so now let's study the difference between compaction and consolidation. Firstly, I'll try to tell you that in compaction, it is obviously an instantaneous phenomenon. As you imply the loading, automatically the air void will be decreased. Okay, but consolidation is a time-dependent phenomenon. Consolidation, what happens is generally, when you apply loading, these are constant loadings which are kept. We keep the loading and allow the soil to settle. How does it settle? Is that firstly it is a saturated soil. Here in compaction we have unsaturated soil. So we don't have any air voids in consolidation. So what happens is it is a fully saturated soil, and under direct loading which are kept for long duration of time, what happens is the water expels out of the system. That is nothing but the excess pore water pressure that is coming out of the system, and therefore the soil and the soil grains come closer to each other and consolidation is achieved. This is a time dependent phenomenon, and compaction is an instantaneous phenomenon. Moreover, here we use saturated soil in consolidation and unsaturated soil in compaction, because we are basically dealing with the decrement of the air voids. Mostly in compaction we use dynamic loading such as rollers and dampers, dynamic, which are provided in particular amount of time, but your consolidation is not dynamic loading, that is static loading, in which you just imply the loading and then allow the soil to consolidate correspondingly. So write down first point. First point in compaction is it is an instantaneous phenomenon, and first point in consolidation is it is time dependent phenomenon. Next, write down in compaction, write down soil is generally unsaturated. Soil is generally unsaturated. In consolidation, write down soil is completely saturated. I have told you why is it. Okay. Next, write down densification is due to reduction in the volume of air voids at given water content. Then write down in consolidation volume reduction is due to expulsion of excess pore water pressure from the voids. There is expulsion of excess pore water pressure. Then write down in compaction, write down dynamic loading like rollers, tampers, etc. are used instantaneously. Okay, here we are using instantaneously, dynamic loading are being used. Then write out in consolidation static loading is applied. Now, so what was happening in compaction was okay, so we can say that in compaction, this is the three-phase diagram before and after consolidation. After the reduction of air voids, the system is now like that. There is no reduction in water and there is no reduction in solids. What happens in consolidation? Water volume is reduced as the excess pore water pressure is taken away from the system and the solids remain the same. So this is what happens in consolidation and this is what happens in compaction. Okay students, now let's look at the phase diagram of the soils after and before the compaction which has been taking place. So initially, if my volume is V naught and void ratio is E naught will be nothing but what? Volume of voids upon volume of solids. So VV can be written as E naught into Vs, this much, and this is Vs. Okay, this is nothing but the volume of voids. Finally, the EF is nothing but this much. That is nothing but VV dash the next volume of voids upon Vs. So VV dash will be nothing but EF into Vs, which I have written over here, and this is the final volume Vf. Okay. Now net delta V will be equal to V final minus V naught, and that will be nothing but is equal to, this will be nothing but the change in this E naught Vs and EF Vs, because net this is nothing but will be equal to the change in the voids only. That will be nothing but equal to E naught Vs minus EF Vs. And if I want to calculate delta V by V, that will be nothing but equal to E naught Vs minus EF Vs upon net volume was what? Initial volume, which we have to consider. So V naught is nothing but what? E naught Vs plus Vs. So E naught Vs plus Vs. So Vs will cancel out, and what we'll be getting is this E naught minus EF upon 1 plus E naught, and that will be nothing but equal to delta E upon 1 plus E naught. That is nothing but delta V by V naught. Most importantly, what I want to say is that here, yes, I got delta V by V naught. Yes, I got delta V by V naught, but we know that the extent of the area, this is the extent of the area is very large as comparison to depth. Because the depth is very small, this might be 10 meters or so, but area is huge. So the change in volume is nothing but change in the height itself, because the area is not going to change much, because that is of huge depth, that is infinite length which we are considering of our soil. So this is nothing but also equal to delta H upon H naught. So this is the formula which I have derived for you, which is very important, will be used in consolidation as well. And because in the consolidation as well, we can say that if we want to remove this air part and then water will be compressed, then also you will get the same derivation there also. So please note down this is very important. Okay students, now let's discuss the next topic, that is the compaction of cohesionless soil. What is the cohesionless soil? Actually the coarse grained soil are called as the cohesionless soil. Why? Because there is no attraction between the particles. As you can see that clay particles are a lot sticky, therefore they have a lot of dry strength in them, therefore they are more cohesive. Okay, but the cohesionless soils are nothing but coarse grained soil. So what happens in the cohesionless soil is approximately around 4 to 5% moisture content. There is just the exact amount of water in the system what creates a capillary tension in the system, and therefore there is your surface tension phenomenon which takes place, and therefore due to capillary action there is a film of capillary which is being created over here. So between two particles of soil solids you will find this layer of water. So this creates bulking of sand, you would have heard. So this is how the bulking of sand happens, because there is a moisture film which is created in this structure which causes the bulking of sand. Okay, please note on this. This is called as the bulking of sand. Okay, therefore this type of structure is formed in which there is volume. As this film is there, so now the soil solids cannot come closer to each other. So this creates a bulking of sand, and this is also known as honeycombed structure. It looks like a honeycomb. It's also a honeycombed structure. Okay, so this is how a honeycomb structure looks like. This is only possible in cohesionless soil in 4 to 5% moisture content. Please write down. In case of cohesionless soil, we have honeycombed structure. We have honeycombed structure formed around 4 to 5% moisture content. 4 to 5% moisture content. Full stop. Honeycombed structure leads to larger void ratios. Now as the honeycomb structure has been formed, what happens is the void ratios increases, bulking of sand happens, therefore the dry density of the system, gamma D, decreases. Understood? And when you put on more water into the system, if you increase the water content more than this percent, this film also breaks. Now the particles come close to each other, then the gamma D starts increasing once again. Okay, so this is how the compaction of coarse grained soil or cohesive soil is taking place. Now as the void ratio of the coarse grained soil is less, but yes, they have voids, size is more. The voids size are more, therefore that is why it has more permeability as well. Void size are more, which implies that vibration is used for compaction. So when you have larger size particles, you can easily vibrate it, and vibration will cause the particles to come closer to each other, and hence it will compact the whole system. So this is how we use, that is why we use vibration techniques in compacting the cohesionless soil. After that, write down, due to bulking of sand, the dry density achieved by compacting the soil is generally quite less. Is generally quite less. Full stop. The honeycombed structure results in the bulking of sand. Full stop. Then write down, bulking of sand occurs due to capillary tension, which brings the soil particles closer, incorporating large voids between a ring of soil aggregation. This is what they are explaining, the honeycomb structure. Next, write down, the fine to medium sand. It should not be gravel as well. This is basically for what? Cohesionless soils, but they should be fine to medium sand, not heavy sands, not large sands or gravel. Okay, it should be fine to medium sand. Right on. The fine to medium sand is generally compacted. In a completely dry condition, or completely saturated condition, because the dry unit weight under this condition is maximum. Obviously, because there won't be any honeycomb structure formed when the water content is less, that is in the dry condition, and if more than that, then the film will break, which I'll be making you understand right now. Next, write down, as the moisture content is increased from the dry condition, bulking of sand occurs at around 4 to 5% moisture content, leading to minimum dry density, and when more water is added, the capillary meniscus, this is called as the capillary meniscus, breaks. Hence, gamma D slowly increases. Okay, hence gamma D slowly increases. Full stop. Then write down, maximum density will be again obtained. Under saturated condition. Okay, so first it is maximum in dry condition, then it will decrease, and then again it will come back to the original value when it is saturated. Okay students, now let's discuss the compaction of cohesive soil. What is a cohesive soil? It is actually sticky in nature because there is cohesion between the two particles. That is why these soils also have the void sizes are less. So in the cohesive soil, void size is less. Void size is less implies vibration cannot be used, because vibration is used when the void size will be heavier. If you can just vibrate the system and the soils will come to closer to each other. But here the soils, the voids are so small that you have to use some tampering or ramming or very pin-like structure which can provide larger stress. So generally vibration is not used here. Vibration is not used. We use a sheep foot roller. A sheep foot roller, you would have heard, this has a very thin applicating area which will be like a pin, which will be providing lesser contact area. This will be the contact area which will be impacted. So the area is now lesser. So if area is less, the force is constant, area is less, automatically the stresses will increase and the compaction and the gamma d will also increase. So this is why for clay particles we use sheep foot roller. It is like sheep foot. Sheep foots are like this. So that is why we use sheep foot roller in this condition. Okay, this is very, very important. Lots of time they were asking in match the following type of questions. Write down. Write down. Vibration does not have any effect on cohesive soil. Vibration does not have any effect on cohesive soil. Full stop. Compaction is done using rollers, tampers, etc. Stop. In compacting clays, position of the particles must be changed by forcing the contact points along the adjacent surface to positions more parallel, thereby reducing the voids. Full stop. Then write down. As we want to apply large pressure at the contact point, we generally use sheep foot roller. For compacting clayey soil. Full stop. In sheep foot roller, large load is transferred over a small area, hence huge pressure is created. Okay students, now let's study the Proctor compaction test. What is a Proctor compaction test is, here we try to compact the whole system by increasing the water content as well as trying to increase the gamma D. So what we do is we keep on adding the water, and at the same time we keep on tampering or providing the dynamic loading as well at the same time. Now what happens is, when I add water, what happens is the system tries to compact under that water, and what happens is, initially when you add the water, small amount of water, what happens is the gradual system change is taking place. So what is happening is, that is providing lubrication or friction between the particles. They slip onto each other and come to a very compacted state. So initially the soil grains are coming closer to each other because of lubrication that is provided by the water, and hence the net volume of the system decreases. Soil's weight, that Ws is constant, therefore volume decreases and the compaction is achieved because the air voids are now expelled out and the system is now compacted. So initially when you add the water, what happens is the system takes the water as a lubricating agent. That what it does is comprises of just makes the soil solids together, and therefore the system is compacted. Now after it, if you try to increase the water, what happens is it tries to take the place what the soil solid was initially. So if you keep on adding water, what will happen? The net water volume will increase, and the system which would have had solids in majority will now have water in majority. So now after some limit, the water tends to break off the whole system and becomes more dominating than the soil solids. That is why your whole gamma D or the dry unit weight decreases. That is why the curve is, firstly will increase up till OMC, that is called as the OMC, optimum moisture content, and then it will try to decrease. This is how the curve is plotted, and after that it will decrease because now in this region the soil is something which has more water in it. That's why this is called as the optimum moisture content, which will providing me the gamma D maximum. Now what happens is, if this is corresponding to some energy or loading which is provided, E1 is nothing but my compactive effort. E is nothing but my compactive effort, and gamma D max is my maximum dry density, whereas my OMC is optimum moisture content. Okay. Now this is compactive energy which is provided in the first case, which is giving me OMC 1 and giving me gamma D max 1. Now what if I increase my compactive effort? My compactive effort is increased. So in the next case, my compactive energy which I am providing is increased. Obviously there will be more compaction, early compaction. So the gamma D max achieved will be higher as compared to this one. Obviously that will be happening. But what about the OMC now? Now if you provide same OMC, what will happen? Water is more and the loading is also more. So if you keep on adding water and if you keep on hitting with a higher load, what will happen? The system will break off. Just try to imagine that particular thing in your mind. So what will you do is, like, when you're increasing your compactive effort, obviously the water required will be lesser to achieve that high point in the dry density. So next graph will be like this. So this will be corresponding to E2. Here E2 is greater than E1, which we are providing, and now my OMC has also decreased. This is my OMC 2, but my dry density, which is the maximum dry density in the next case, this is gamma D maximum 2, will be greater than the gamma D maximum 1. So So what can I make up from here is like gamma D max 1 is less than gamma D max 2, OMC 1 is greater than OMC 2. So this is what you get when you increase your compactive effort in a system, and this is due to the lubrication theory which I have already told you. Please write down. As per Proctor, definite relationship exists. Definite relationship exists between the soil moisture content and degree of dry density. Soil moisture content and degree of dry density. What is it saying? It's saying that there is a proper connection between moisture content and gamma D. Okay? To which the soil can be compacted. Again, I'll repeat it. As per Proctor, a definite relationship exists between the soil moisture content and the degree of dry density. Okay? To which the soil can be compacted. Next, write down. At low moisture content, soil is stiff and more resistant to compaction. Soil is stiff and more resistant to compaction, full stop. As moisture content increases, because of lubrication, the soil particles can easily move and become densely packed. This is what I'm saying. Initially what happens is, when you add the water, small amount of water is added, the soil particles move easily, freely, they are lubricated now. So what will happen? They will move freely and they will move to a denser state. Okay? Then write down, but the effect of lubrication is beneficially completed up to OMC. Up till OMC, it is beneficially completed. Next, write down, beyond OMC, water starts occupying the space which could have been occupied by the soil grains, hence gamma D starts decreasing. Beyond OMC. Hence, gamma D starts decreasing beyond OMC. Now, I want to tell you one more thing over here is like, this is the Proctor compaction test. So, this is, for example, a OMC chart. This is nothing but the water content chart in comparison to gamma D. So, OMC is this one at which the maximum dry density is being achieved. Now, this is a moisture content, this is nothing but a water content. Now, what must be happening is, at this water content, that does not mean that saturation is 1. It is fully saturated. It does not mean that. There will be some amount of saturation, that might be 0.7, 0.8, 0.9, 0.6, whatever that would be. So here, what somebody told that, okay, at this point, what if the system is achieving saturation? So the maximum, the most, or the theoretical maximum dry density would be that at particular moisture content, that might be this moisture content, this moisture content, this moisture content, that will be that, not corresponding to this graph. That would be somewhat when you have removed whole of the air voids, and at that water content only, not by adding more water content. At that water content, if you remove, so two things will happen simultaneously. What will happen? Your water content will be very optimum, will be very applicative to the system. Moreover, all the voids are being removed from the air. So we will have a theoretical dry density graph. This is corresponding to the water content itself. This is called as the zero air void dry density line or a curve. This is a curve. Now here, whatever we will achieve correspondingly will be nothing but this will be giving me gamma d theoretical max. Okay, there is a difference between gamma d max, that is corresponding to OMC, but gamma d theoretical max is nothing but at any moisture content. If you want the theoretical maximum dry density, you have to saturate the sample at that particular point. Okay, this was the basics what I taught you. Next class we'll be discussing problems on this topic. Thank you.